So 3-6 is the mathematics of finance, and what we're up against is always truth in lending. You know, if you go through life and you never have to borrow any money, good for you, but you'll be one of the very few. When you purchase a home and you hear about the APR, you know, whatever the annual percentage rates are for a mortgage, sometimes you get excited, sometimes you get a little depressed, you know. Record lows for mortgage interest are behind us. The mortgage rates have started to go up a little bit now. I believe standard is 4.25%. And that doesn't sound like a whole lot, you know. So you think, gosh, 4.25%, that's a pretty good lending rate. $200,000 house is not out of the question in the Elk River area. So you go out and you're looking around and you find something for around $200,000. And you see the interest rates are at 4.25, which is not the most they've ever been, but it's pretty good. And you sit down and you start figuring stuff out and you realize, oh my gosh, if I paid 4.25% over a 30-year mortgage on this $200,000 house, I would be paying close to $450,000 for this. Because the amount of money you're borrowing is so large that 4.25%, it builds up. You're talking 30-year mortgages. So those are things you have to consider. Sometimes you don't want to. I'm one of those people that don't really want them to give me all of that information because I can do the math myself. And so I actually get physically ill. There have been times when I've had to walk out of the finance situation on a vehicle because I had to go throw up. I just think about all of that money and it just makes me physically ill. So it's one of those things we need to think about, but maybe not think about quite as much as I do because it just makes you upset. So what we want to do is compute interest on investments. See, now there's a good thing. You put money in, money comes back. Unfortunately, the rates for that right now are just sickly low. I looked them up last night so I could tell you normal savings accounts, the APY right now is at 0.06%. You hardly get anything back on your own money in the savings account right now. If you happen to be the member of a credit union, you can get 0.1%. Look at that, 0.1% for the course over here. You know, and it has always been that way. You know, if you want to save money, the rates are always much lower than if you want to borrow money, and that's why banks are in business. That's how they get their money. So we want to know if it's compounded annually, what would you get? Compounded K times per year, because honestly, most savings accounts now are going to be compounded each quarter. They're not going to wait until the end of the year. It will be quarterly interest. And then compounded continuously. And then we want to find annual percentage yield, and we'll actually try and do that today because if you've forgotten, I haven't, but we have a 2-hour early release on Monday. And so I'm going to try to get a little bit more in today than we normally would so that we have a little half hour on Monday. We can finish up what we need. Determine the better investment. Absolutely. You know, they don't all have the same interest rates. They don't all have the same compounding periods, and you want to know where should your money go? Where will it best serve you? Then on Monday, we'll talk about calculating the future value of annuities, and that would be how much money will you have at the end of all of these years. And then we're going to find the monthly payment on something like a mortgage. Find the term of the investment, knowing monthly payment and the future value of that. Calculate the present value of loans and mortgages, and then determine your monthly payments with that present value. So we'll know the math behind it. So as we have a couple of quotes down here, the mathematics of finance is the science of letting your money work for you. If you have a lot of money, it's a very good thing to do. Time is on your side by the Beatles because it truly is. If you leave it sit in there, good things will happen over long periods of time. Sometimes you have really good interest rates and sometimes not so good. So the mathematics of finance, we're going to talk first about interest compounded annually, which is very basic. You started learning about this back in exponential algebra. Interest is the cost that we have to pay when we borrow money. You need something, you don't have the money for it, but you have good credit. You know, it's It's the interest we have to pay. Interest is a benefit we receive by making investments or by putting money into savings. So since savings accounts are so low, people are getting into buying CDs more. Many people are now into investing in the stock market more than ever. It's just, if you want to get good rates, you have to shop around. So if we have interest that's compounded annually, we have a great formula for that, and it's a nice little formula we've actually looked at this year, where A, capital A, is the amount of money that you accumulate. P is the principal, and that is the banking word for the initial amount. What did it start with? And then R, of course, is the interest rate as a decimal. Whenever we put things in the math formulas with percentages, we change it into a decimal. And then N is the number of time periods. In this case, we're talking about years because we just have a little annual formula. Now, it's not very large until we get down here. It is up here in this table. And again, very similar to the one that we had in Algebra 2, just using different letters. That's all it is. So, we're going to find all of this information. One thing will be missing, and it's our job to find whatever piece is missing. So, this is the constant percentage growth pattern that we studied in section 2. And the value of an investment is an exponential function of time. Hopefully, the longer you leave the money alone, the more money you make. Compound interest is interest earned on interest. So if your bank says we have compound interest, what they're telling you is they're going to figure out how much interest you've earned at the end of 3 months, because usually it's quarterly. And then they'll calculate your interest off of that new balance. You don't constantly go back to the original amount of money and just always get the same amount every time. So compound interest is interest earned on interest. Interest compounded annually if the principal P is invested at a fixed annual interest rate R calculated at the end of each year, so annually, then the value of the investment looks like this. Most basic example we have talking about interest. A equals P times 1 plus R to the N, where R is expressed as a decimal. So compounding annually, we've got a formula, and we've got a nice example right here. It says, suppose Quan Lee invests $500 at 7% interest compounded annually. Find the value of her investment 10 years later. Now, thinking ahead to your assignment, you're not going to know which ones are annual, quarterly, monthly. So the first thing you should do is find that information in the problem so you'll know which formula you should be using. And if it does say annually, well, then we can just go with this little one. Which is nice because it's the smallest formula we have. So she put $500 in. Where's that supposed to go? P, principal. 7% interest compounded annually. What do we change that to? 0.07, and where does it go? R. Find the value of her investment 10 years later. Where's the 10 going? And number of years. This is a punch it in problem. Love it. And certainly we could simplify 1 plus 0.07. But punch it in. That's all it is. Let's find out how much money Quan Lee can expect to have. 500, 1.07, parentheses. Oh, that's not one. She'd love that, wouldn't she? 1.07. There we go. To the 10. $983.58. But I have bad news for you. Banks always round up. We're going to go ahead and round up because that's the answer the book wants. But if you go at the end of the year to collect your money, they will round down to $983.57 because it's their money. You know, and they don't want to give it to you. They don't want to give it up. But if you're a very cute kid, you might be able to get that extra penny off. You go back at the end of the year and say, oh, I was saving so much money, I had so much money in there. Could I get my $983.58? Look, I figured out the math with the help of my mom. But the rest of us, it's no, it's our money. That's how we do it. Alrighty, so there is the annual interest for Quanley, and I would suggest she find a new bank, because most banks do quarterly interest, not annual. So interest compounded K times per year is where she wants to go. You want to figure out who's offering what and check out the interest rates. But again, sometimes when you go from interest compounded annually to quarterly, they lower the interest rates. So you have to watch out and see how they work out with the formulas. So this looks a little more complicated. It's not too bad though. The only thing we're adding in here is the K. And the K stands for how many times a year this is going to be compounded for our interest. And for most banks, like I said, it's going to be a 4 for quarterly. But some will go to monthly. It's just a matter of how much money you have. The more money you have, the better you can negotiate for your stuff. If somebody walks in and says, I want to put $4 million in your bank, they're going to negotiate with you. They want your money. And that's because for every dollar of your money that they have in the bank, they can lend out $3 to somebody else. And that's where they make their money. So A, amount accumulated. Still going to be our final amount. P is still principal, still have the 1 in there, so we get 100% of the original, plus the interest rate as a decimal, but this time we've got that divided by K because we have to divide that annual interest rate by how many times a year they're going to give us that. And then the KT up there, number of compounding periods. When we were studying earlier how sometimes to figure out how many times things were compounded, we had to figure out the time periods for weird situations like bacteria that doubles every 20 hours. This is the same kind of thing. You have to say, well, how many times is this going to happen? If 4 times a year they're doing this compounding business, and I'm going to have it in there for 5 years, well, that would be 20 compounding periods. So, compounding monthly. Somebody's gotten a good deal. Suppose Roberto invests $500 at 9% annual interest, compounded monthly. That is compounded 12 times a year. Find the value of his investment 5 years later. Okay, well, $500. 1 plus, what's going in for R? 0.09 divided by, how many time periods a year? 12. So that 12 goes back up there as well. And then how many years? 5. All right. So we're going to punch her in, see what we get. And I always follow the order of operations. I know the calculator can do this too, but I'm going to do the division inside the parentheses first. I guess I'm just not that trusting of my calculator. And add 1. Raise it to the 12 times 5. If you want to do that, you have to get 60. You can do that, but you wouldn't have to. The calculator will do that for you as well. And then take that times 500. Because what we don't want to do is round anything as we're going through this. We want to be able to just punch it in and get it all at the end. So $782.84. And there it is. So those were 2 really straightforward problems where we have all the information that we need. And we can figure out how much money we've accumulated. But now, this one's going to have us work backwards a little bit. And it says we're going to find the time period of an investment. Judy has $500 to invest at 9% annual interest compounded monthly. How long will it take her for her investment to grow to $3,000? So she's got something she's saving for, and it's around $3,000, and she wants to know how long this is going to take. So this time we know what we want accumulated. We know we need that to be $3,000, but she's starting with $500. got that 9%, same as Roberto up there, monthly. We don't know. That's what we don't know. But we do know how to solve this. And what we might want to do is just stop and see, is what we have in the parentheses something halfway decent we would want to write down, or 0.09 divided by 12 plus 1. That's not too bad. Simplify it a little bit. Oh, 1.0075. 12t. We have an unknown exponent. We're going to have to use logarithms at some point. So, what would you do first? Divide by 500. Okay, what's 3,000 divided by 500? 6. Good, that's a nice number, like that. Now, we're going to use natural logs. Remember, we're supposed to get more and more use out of those natural logs. So we're not going to do logarithm base 1.0075. You get the same answer, but we need to get practice with natural logs. So natural log of both sides, natural log of 6 equals natural log of 1.0075. Notice I left some space, because what would I do with that 12? Bring it out in front. Yeah. Make this multiplication. So how would you start to get the t by itself? Yeah, get the natural log over to the other side. Time equals, let's see, natural log of 6 divided by natural log of 1.0075. Divide that whole thing by 12. 19.983. But here's something I'm absolutely going to tell you, and we will absolutely use, and that is, they will not pay that until the end of the year. That's how banks work. You have a contract. You have a contract for a reason. You don't earn that money unless you leave it in there to the end of the entire year. So this is not going to come to her until 20 years. If she wants $3,000, she has to pay until the end of 20 years. At the beginning of yes, it would be enough. And what banks are going to do is they're going to constantly push to keep your money in. They want your money so they can borrow more money out to other people and make it, So that's how they do it. Even if it's compounded quarterly, let's say you go in halfway through the year, and again, sometimes just to be nice, if it's a child that's learning how to use a savings account, they'll actually give you the money for halfway through the year. But for most of us, if we go in, they're going to say, well, this is mid-year, you're going to lose the interest from the first 6 months of this year. And if you need the money, you need the money. It's just one of those things you have to consider. So they always wait until the end of the year to tack on that last year's interest. Finding an interest rate. Stephen has $500 to invest. What annual interest rate compounded quarterly, which is 4 times a year, is required to double his money in 10 years? Well, this is interesting. Let's see what we can do with this. All right, $500 to invest. 1 plus, don't know the interest rate, but I know that it's going to be quarterly. And he needs to double his money in 10 years, so 4 times 10 up there. If he doubles his money, how much will he have? $1,000. Now, if you think about it, the first step tells us what's going to happen anyway. Because we would go ahead and divide both sides by 500, and it's not magic that gives us this 2. We were trying to figure out when it's going to double. It's going to look like that. That's getting interesting, huh? Okay, so what do you think we should do? Natural log. What do you want to do? 40th root? Well, good luck with that. 40th root, that's, yeah, we should definitely think of another way to do this rather than 40th root. So let's take the natural log so we can get that 40th root business taken care of here. That way we can bring the 40 out in front. And then we'll like so. Okay. What should we do next? Division. Looks like so. Well, I don't like that natural log there now. Now it's messing up the words. How do we get rid of it? E. That's how we get rid of it. E to this power. E to this power. This is getting interesting. Better. What would we do next? Subtract a 1. Oops. Almost look like an equals. And finish it up by doing what? Well, this looks like fun punching this in. All right. Let's see what we can do with this. E to the natural log of 2 parentheses divided by 40 parentheses minus 1 parentheses times 4. Boom. There it is. So we have R equals 0.699187684. I didn't need all of those, but I wanted to talk about this in terms of percentages. So what should we write down if we go to decimal places? Percentage. 6.99 what? 2. There it is. That's the interest rate that she will need to look for if she wants to double her money. Now, if she absolutely has to do this in 10 years, she would have to round that up a little bit. She'd probably have to go with 6.993 just to make sure that she has the amount of money that she wants. Again, with the amount of money she has, she's not going to have a lot of bargaining power. It's only $500. So she probably better plan on leaving the money in a little bit longer. If she can get around 7%, that would be great. Because then she'll be sure to have that money doubled in 10 years. And we can do 40th root. But if you do 40th root, the chances that you're going to get numbers that the calculator says, oh my gosh, I can't do this, are really high. You know? I would say if we had ended up with something for maybe 20 or less for that power, we would be okay. But the 40th root, well, let's check. Let's question it in. Did it give you 40th root? Did it? Okay. So the reason we do this is because once you reach a certain height with those powers and a certain number, your calculator kind of freaks out and says, oh, I can't do So, more accurate to use the natural logs. Yes. Exactly. Yeah, because order of operations says we would have to do this first before we could raise e to that power. So, and there's a lot of different ways to get the correct answers. It's just, are you working with a graphic calculator, a handheld? It has its limitations. Are you working with a computer? Because in banking, of course, all of this is going to be computerized, and they're going to have software for it that's going to handle all these large decimals. So, however we can get to that answer using the right math, be all right. All righty, interest compounded continuously. Yeah. Oh, the boxes that are up here that they have on here are just for you if you want to check these graphically. You know, using your graphic calculator, you could certainly do that with the intersection, y sub 1, y sub 2, all of that good stuff. But most of the time, the algebra is pretty straightforward, and we can get it from there. So this says, what would happen if we increase the number of compounding periods boundlessly? And we talked about this before. This is Leonard Euler, and Leonard Euler was trying to be a loan shark. And he said, hey, if I could charge interest to people all the time, so if they came up and said, I want to pay off my debt to you right now, how much do I owe you? He would say, do you want the amount that you owed me when you first asked me this question, or the amount that you owe me now? Maybe we better talk about the amount you owe me in 10 minutes, because that's going to be even a little bit more. But what he found out was, because money is to 2 decimal places, even if you increase this to 100,000 times of compounding, at a certain point it reaches a limit. And that's, often hard for people to see. So let's take a look at this graphically, and we'll see what happens. So if we were to graph this, we'd have 1,000, parentheses, 1 plus, parentheses, 0.1 divided by x, parentheses, parentheses, so that we've got all of that in there, to the x power. And think about the window, and we're talking about years that this money would be in, or actually in this case it could be seconds, because this is continuously, but I just put 30 years up there, and since the initial amount was 1,000, I put 1,500 in there to see the growth. And if I hit graph, initially you think something is wrong with your calculator, because this is exponential. This should keep going. It should keep getting higher, but it doesn't. It levels up. And if we go to our table, we see that. At first, it gets bigger, but we notice it's not making a whole lot of change, and we are at lots and lots of time periods here. In fact, this is going to level out eventually to $1,105.17. And that's because Euler discovered that you could really replace this with E, his number, E, 2.718, blah, blah, blah. So that's what happened. Like it says, recall from section 3.1 that the limit of that 1 plus 1 over x to the x is really E. That's Euler's number. That's what was discovered. So therefore, for a fixed interest rate, if we let x equal k over r and we graph this whole thing, this really comes down to E for this portion. So that brings us to our stinky green shampoo formula. And the stinky green shampoo. Hey, Bert. Stinky green shampoo formula. And that's the formula we use for continuously compounded interest. So, compound interest down here, it says the value of an investment. Well, notice we've got 2, because this is compounded k times per year, which is the one we already looked at, quarterly, monthly, even daily, 365 in there for k. But when it's compounded continuously, sometimes it's worded as continuously compounded, sometimes it's compounded continuously, but look for those 2 words together that's the Stinky Green Shampoo formula. That's the one we use. So compounding continuously, who gets that? People with lots and lots of money. They bargain for it. You know, that's just what they do. Hopefully, you might experience that someday. You know, that you have enough money that you can go in and reason with the bank and say, I want to put this huge amount of money in, but I'll only do it if you give me continuously compounded interest. You'd have to have a lot of money to make that happen. Suppose Latasha invests $100 at 8% annual interest compounded continuously. Find the value of her investment at the end of years 1, 2, blah, 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 all the way to 7. Well, all right then. Stinky Green Shampoo formula. So she has $100, and we are going to find the different time periods. So we could put a 1 in there for tea, punch it in, put a 2 in there for tea. It'd be kind of silly. We've got a graphic calculator that'll give us a table for it. So why not take advantage of that and have our years over here? And then the amount of money. And as long as we see enough decimals to round appropriately, that's all that matters. So y equals 100 e to the 0.08 x power. And I probably have my table way up there in no man's land because of what I was doing with investigating Euler's numbers. So I'll do second window table set and tell it to go back to about 0. That would be a good place to start it. And second table. And there we are. So it is rounding to 2 decimal places, and that's all we want to see with money. So after 1 year, $108.33. After 2 years, $117.35. After 3 years, $127.12. After 4 years, $137.71. 5 years, $149.18. 6 years, $161.61. And 1 more year here, $175.07. And yes, of course, you could graph this. You know, you could use years for X. But if you just want to see the individual numbers, the table is the best way to go. It wouldn't be horrible to plug the numbers in here because once you had it in with the parentheses in the right place, you could just do second enter and replace the one number. So that wouldn't be awful. And that's what we have to do if we can't see that rounding to 2 decimal places. So if the numbers are larger and we know it's not going to fit within that y sub 1 that we have up there, then we could put them in. It would be awful, but it would take a little bit more time. So now, objective-wise, we are ripping through this stuff, computing interest on investments annually, multiple times per year, and continuously. Out of the way. The other one we want to deal with today is APY, not APR. Not annual percentage rate, annual percentage yield to determine the better investment. Yield is what you get at the end of that time period. So the annual percentage yield, the APY, the percentage rate that compounded annually would yield the same return as the given investment rate with the given compounding period. Oh my gosh, what are they talking about? They're saying, you're looking at all the ads in the paper. This bank offers 3.75% compounded monthly. This one offers 3.6%, but compounded daily. And you want to know which of those is going to be the better deal for you. So you think about how many years you're going to leave that money in, and you do the math and you figure it out. So finding APY allows us to compare 2 different interest rates and compounding periods in order for us to determine which one we want to use. Better for us. So use this relationship to determine APY, and APY is going to be X in this equation. APY does not depend on the principal. The amount of money you're putting in makes no difference. It's just going to divide out of the formulas anyway when we try to compare them. So you'll notice that looks really familiar. You know, that's our compound interest right there. And on the other side, all we need to determine APY is little 1 plus x. That's it. So if we can get this and subtract 1, we'll have it. And some books literally have that as the formula for APY. I do like this way because I really think that it makes you focus on the fact that this is about the interest, what you're getting, and that we have that 1 plus x on the other side. So the annual interest rate charged on consumer loans is the APR, and the APY for the lender is always higher than the APR. And this again is because of what we've been talking about as far as, banks always rounding up, taking advantage of that extra penny. And you think, gosh, how cheap is that of a bank to hang on to my extra penny? Why wouldn't they give me that? Well, imagine the other 300,000 pennies that they are getting at that same time from everybody else. It's money, and they're in the business of money, so that's what they do. Computing the APY. Ursula, oh my goodness, there's a name that brings us Little Mermaid memories. Ursula invests $2,000 with Crab Key Bank. Oh, they did that on purpose. At 5.15% annual interest compounded quarterly. All right, it's bad. It's not as bad as Leg and Sickle baking soda, but it's pretty bad. What is the equivalent APY? So let's get used to our wonderful little formula up here. 1 plus x equals 1 plus r over k to the k. And see what we have. So she invests $2,000. We need that information. Not for APY. That's not important. Remember, it would just divide out if we're comparing anyway. 5.15% annual interest. Where should that go? It's still R. We're going to put it as a decimal though, so that'll be 1 plus 0.0515. Compounded quarterly. What are we going to use? 4. What is the equivalent APY? You're kidding me. That's all we need. That's all the information that is. That's all the information we need. That we can just punch in and subtract the 1, and we've got it. Like an APY. Nice little formula. So 0.0515 divided by 4 plus 1 to the 4th power minus 1. And there it is. So what was the equivalent APY? As a percentage, what would it be? 5.25? Yeah, we'll put the 0 on there just to make sure everybody knows that we know how to go to 3 decimal places. So 5.250. Did that match the APR? No, and they mentioned that earlier, that the APY is always going to be, the yield will always be a little higher than the APR is. So let's see. Down here, this one says we want to compare 2 of these. So somebody's shopping around, got some money to put in. Which investment is more attractive? One that pays 8.75% compounded quarterly. How many times a year is that? 4. Versus another that pays 8.7% compounded monthly. How many times is that? So we'd definitely be interested in which one of these is better for us. Which one is a benefit? So 1 plus x. Oh, I better label it. We'll have this one be the 8.75%. Right here. So 1 plus x equals 1 plus, what do we put in there for r? 0.0875. And at the 8.75%, how many times is that going to be compounded? 4. So again, really, we could just subtract 1 from that, and we'll have what we need. punching away. You let us know when you've got it. What do you have for your APY? Everybody thinks they got a wrong answer. Everyone wants to share. Somebody share. 9.041%. That's exactly what it is. So as a decimal, it came out to 0.09041. Probably better put that on here so when somebody looks at the notes later, they're like, where did they get that from? From right there. Well, now we need to look at 8.7% compounded monthly. So 1 plus x equals, and notice I'm not using the parentheses for the left side. You know, it's kind of nice that they put that on there to group those together for us so we can see it's 100% of the original plus that rate. But for the math portion, probably don't need it as much. So 0.087 divided by, what did you put down there? 12 compounded monthly. And then we do our subtracting 1. Are you done already? What'd you get? 9.055%. So 0.09055. So these guys had the higher interest rate, the highest of the two. What would that be the one you would go with? Which one yields more? Monthly, yeah, the monthly interest. So, which investment is more attractive? 8.7% compounded monthly is more attractive. There it is. So that's the second piece to our objective. Again, half hour on, oh, yes. Put the negative one at the end? Yeah. Absolutely. Absolutely. As long as we understand what the formula is doing, we're fine. Like I said, what they're trying to get across to us is we want to see 100% of our money plus whatever that APY is equals that interest piece that we have over here. And it's mostly because this formula has that original 100% in there too, that we want to take that out of the picture and just look at the percentage. So yeah, I kind of get that way too, where I cheat and put that over there. And absolutely, that's okay, because once we understand the math, that's the good part of it. Alrighty, we will save calculate the future value of annuities. Do you guys know what an annuity is? That might not be something you've ever heard of before. If somebody gets into a major car accident and they get a huge settlement, generally that's paid in what are called annuities. They don't give them $12 million all at one time because they can't afford to do that. So they give them an annuity instead. So hopefully none of you will ever experience an annuity. That's usually a bad thing. It's very rare that an annuity is a good thing. Find the monthly payments in terms of investments. Yeah, that would be good for mortgage. You can see, is the bank calculating everything right here? Because bankers are human beings too. You know, they punch in the wrong number into the software. The way to go. Oh, you don't need this one yet. You need to uncover that one. And the top one, you're probably not going to see any APY assignment because in the past we split this up with just the normal compounding formulas the first day, and then introduced you to all the new stuff the second day. But as I said, we have an early release, not very well scheduled for Monday. Finals week, probably not the best thing in there. But to our early release, a couple of days of review. We'll be ready for Chapter 3 test. Good stuff. Real life stuff.